Hi, folks. We're back to look at the last questions of your final review. This first question here says Carla knows that 1 liter is equivalent to 1,000 cubic centimeters. Well, this is a cubic centimeter. This thing is a cube with 1 centimeter on each side, and it represents 1 milliliter of water. What's really interesting is that it happens to weigh 1 gram if it's water. These things are neutrally buoyant, which means they weigh the same as water. This is a really good example of 1 milliliter, 1 cubic centimeter. Now, if I take 1,000 cubic centimeters, that's a 10 by 10 by 10 cube, for example. I don't happen to have one on handy, but I do happen to have one of these. And just to give you an idea, if I take a look at how many cubic centimeters are in here, I know I need to take the area of the base, which happens to be this base right here, and it's 3 by 4. So there's 12 of these little cubes that would fit in the bottom of this base, and it would look something like this. And so I would have 12 in the bottom of this box. And then if I added another layer, I would have 24, another layer, and another layer, and another layer, which is why we take the area of the base times the height. And this happens to be 5 high, and its base holds 12 cubic centimeters. So the whole volume is the area of the base 12 times 5, or 60 cubic centimeters. There are literally 60 of these little cubic centimeters inside this. Now, the question in this one, it says that we have a cylinder, and we can find the volume of a cylinder in much the same way that we find the volume of a prism. We take the area of the base times the height. Now, it says, what method would we use to find the maximum number of liters of water a cylindrical container will hold? Well, if we know its dimensions in centimeters. Now, clearly this isn't drawn to scale, but I'm going to give it some dimensions here. Oh, sorry, it's a pretty funky looking cylinder. Anyway, it's supposed to be straight up and down. Let's give it a radius. Let's make it really easy. Let's give it a radius of, say, 10. Make it really simple, 10 centimeters. And let's give it a height of, I don't know, we'll make it 5 centimeters is the height. So if I were interested in finding out how many cubic centimeters it has, I could use the formula. The volume of a cylinder is equal to the area of the base, that's the area of this circle down here, which is pi r squared, times the height. And in this case, we're talking about pi times 10 squared times the height, which is 5. And this is going to be 100 times 5, or 500 pi. Now, this is in cubic centimeters. That's how many of these would fit, more or less, inside of this cylinder. Well, that's an exact answer, and we pretty much want an approximate answer. You could change this to 3.14. If you use the pi key in your calculator, it'll become even more accurate, because if I use the pi key, which is, let's show you where it is right above here in blue, that's going to be very accurate. So I could take 500 times pi. Helps if I turn it on. I'm going to take 500 times pi, and that's going to give me about 1571, more or less, 1571. Now, this is actually accurate all the way out to the 7. If I were to use 3.14, it wouldn't be as accurate, and it would give me 1570. So either way, it works out. I'm going to say approximately 1,570 cubic centimeters. Now, these are also milliliters, but it says up above that 1 liter is 1,000 cubic centimeters. So for every 1,000 of these, I get 1 liter. So this is going to be 1.57 liters. What I did was divide by 1,000. and dividing by 1,000 moves the decimal 3 places. Lots of ways to think of that. The best way to think of it is that if you take 1 liter is equal to 1,000 cubic centimeters. It's called dimensional analysis, and it's a really great way to simplify. And you'll notice that I've got 1,000 in the denominator, and it's being divided into this 1,570. The cubic centimeters cancel out, and I end up with liters. So this is the process I followed. Now, what I would like for the students to do is to do something very similar in the Canvas, and on the multiple choice, they give you the steps, the same steps that you would follow to do this. All right, so make one of your own. Don't use my dimensions, please. All right, number 6. It says we have a spherical stretchy ball is inflated to 18 inches. Here's my stretchy ball. And over 1 week, the ball deflated to a diameter of 9 inches. Now, it might look like it's half as big, and it is as far as direct dimensions are. But what we want to know is what percentage did the ball lose? What percentage of its volume did it lose over the week? So this is called a percentage change, and obviously it's a negative. It's went from here to here. Now, you can't just assume that because it's half the size that it's going to lose half its volume, and it doesn't. What you're going to have to do is you have to find the volume of the big ball when it was large, which is, of course, if you know the volume of a sphere, it's equal to 4/3 pi, and I'm going to use the big capital R for this one, cubed. Now, a couple of things to keep in mind. First of all, the 18 is not the radius. This is the big diameter, and you're going to have to get the radius from that. To get the volume of the smaller ball, I guess I could have done it in another color. It's all right. I'll just use a little r for this one. Pi little r squared. You're going to use this is the little diameter, and you're going to use the little radius in this one. Then you're going to find the two volumes and compare them. And in order to find the percent change, you take the new volume, that's the small one, minus the original volume, divided by the original volume. So I'm going to take the volume that I get right here, I'm going to put it in here, and then I'm going to subtract the original volume from that, and then I'm going to divide by the original volume. And what that'll give me is what's called a percent change. This is going to be a decimal change. Now, some people put the times 100 so that the percentage would be expressed as a percent instead of a decimal. I prefer to leave it as a decimal change and just read the percent from it. Your choice. Again, if you want to look up percent change, you're certainly welcome to, but you're going to put in the radii, which it's not this, it's, the radius is half the diameter. You're going to put in the radii, you're going to evaluate them. Be careful when you put 4/3 in your calculator, make sure that you put it inside parentheses. You could use 1.333 and you'll be more or less accurate. Be slightly off, but it's not a big deal. Anyway, hope that helped, and I hope you'll try it yourself. Again, you have to work it out. Don't just write down what I write and just hope to pretend like you know what you're doing. All right, you can put the work down here. Number 9. Manuel and Cindy want to find the volume of a right cone. Manuel measures the height as 10 inches and a radius of 6. Cindy measures the same height, however, she believes 6 inches represents the diameter. Which of the statements below must be true? So what I'd like you to do is just go ahead and draw Manuel's cone, which he says has a height of 10 and a radius of 6 inches. This is 6, obviously not to scale. I'll call it big R. 6 inches, and the height is 10. And then you could also draw hers, which she believes that the 6 inches represents the diameter. So it's going to be half as big because it's going to have a radius of 3. So this is going to be Cindy's over here. It's going to be quite a bit more. It's going to have the same height, of course. It's going to have a height of 10. But this time it's going to have a radius, and I'll use little r, is equal to 3 inches. And we're going to compare the two volumes, so you should find the volumes of both of these guys. And then you'll be able to see which of the statements must be true when you look at the multiple choice. Okay, let's take a look. Oh, we got a nice little pyramid back here for question number 10. And they want me to find the height. Now, I have a labeled diagram. That's my first step for problem solving. The next step is to write a formula. Well, the formula for a pyramid is the volume of a pyramid, write a funky looking pyramid there, is equal to 1/3 the area of the base times the height. Well, the area of this base is 10 by 10. It's the area of this square down here. So we're looking at 1/3 area of the base. By the way, I wrote the formula. That's my next step. That's step number 2. So my first step was a diagram. Here's my first step, diagram. My next step is formula. My next step is to substitute inside parentheses. This is my substitution step. And the volume, they tell me, is 400 cubic feet. And the area of the base, of course, is 100. And what I want to do, and I don't like using a little h for height because this literally is a 3-dimensional height. So I use capital H, but it's fine, whichever one you use. And you're going to solve this, which means getting this number and dividing on both sides and finding your h. Notice that that is the solving step. Well, actually, step 4 is to simplify. And one way to simplify this is to take the 100 and multiply it by the 1/3. You could take 100 divided by 3 and then divide on both sides. There is an easier way to do this, and it's you wouldn't have to have a calculator. You could just multiply both sides by 3 to get rid of the 1/3 and then divide by the 100. Your last step, which of course is the solve step. These are the 5 problem-solving steps that I've been going over all year. All right, last one. Volume of a sphere is 12 pi cubic inches. Sorry, it's kind of funky looking there. There we go. And we've got a sphere. I'm going to make a diagram here, put a belt around it. And do we know the radius? Nope. Didn't say the radius. If the radius of the sphere is doubled, so if I do a bigger sphere, and this is big R. So this one is twice as big, which means it's twice the radius. What I can do, it says that the volume of the sphere is 12 pi cubic inches for the small one. So the volume of the small one is 12 pi, and if the radius of the sphere is doubled, what is the volume of the new sphere? You could just simply guess. I don't recommend doing that. What I recommend doing is actually analyzing this. Follow the problem-solving steps, which is I have a diagram, I have a formula. The volume of a sphere is 4/3 pi r cubed, and I don't know the radius, but I do know the volume. It is 12 pi. What's really nice here is that this pi right here will cancel with this pi over there. In other words, I can divide by pi on both sides. That would be my first step. Now, in order to finish solving this, I need to multiply by the reciprocal on both sides. That's the 3/4. That gets rid of the 4/3 for me. And then I'm going to take what's called the cube root. The cube root of a number is the number multiplied times itself that gives you what you get over here. It's going to work out fairly nice. No, it doesn't work out really well. Now, in order to take a cube root, there are a couple of ways to do it. Yeah, show you how to do this. On your calculator, the way to do it is to take some number. Let's say, I don't know, if I want to take the cube root of 100. Well, let's take the cube root of 8 so I can talk about it. 8. And I'm going to raise it to the 1/3 power. When you raise to a power, it looks like this. It's this little caret key here, or up arrow key. And I'm going to take it to the 1/3 power. So I'm going to put 1 divided by 3 up in there and hit enter. That's 2, because 2 times 2 times 2 is 8. If I take 27 raised to the 1/3 power, it's going to be 3, because 3 times 3 times 3 is 27. 64 to the 1/3 power is the cube root of 64 is 4, and so on. You're going to take the cube root of that number. It's going to give you the new radius. Now, you're going to double it and then find the new volume. Now, this is the hard way. If you really consider putting this into this formula and seeing what effect it has, that's an even better way to do the problem. So good luck on that. I hope it made sense to you and you're able to do it. And I will see you back when you're done. Bye.